in this seminar and in my PhD thesis. So I will start by discussing one of the first works in this domain, the work by Mark Ribert and his colleagues at MIT. So what Mark Ribert proposed was a control scheme to control a single-legged hopper with a leg, control a single-legged hopper. So in this diagram, the blue link is the leg, and the black link is the torso of the robot. It's supposed to be the torso of the robot. And what he proposed was a three-part control scheme. The first part controlled the hopping height. The second part was to control the forward velocity, for which he did not choose a model of the system. He chose some heuristics based on what he observed for the system, and based on those heuristics, he defined a certain position of the foot with respect to the hip of the robot, and so this position of the foot depends on the current velocity, the desired velocity of the robot, and this position was then converted to the hip angle, and then the hip angle was tracked using a PD controller or servo. The third part of this the control scheme was handling or controlling the body attitude. That was quite similar to the servo hip angle, where it was not calculated, it was given that they wanted to maintain a particular body attitude, and they tracked it using a PD controller. So, system that is to the yes. So since X is written in terms of the coordinate system attached to the robot, they use XF. This is fine, but they're in the first position. Yes. Velocity. So this is from the condition that is because I don't understand how that has been. Yes. How that is XF. Yes, sir. This is completely heuristic approach. Completely heuristic approach. So there is no model, even kinematic, that is being. So yeah, from what they could observe and what they did observe. So they did some earlier experiments with robots that have multiple spokes instead of wheels. So H dot is the velocity of each point in the body. Yep. The torso. Yeah. So it is based on that, and if your foot is at 0 velocity, if the torso is moving forward in that, so relative to that, what is the rotation? Something like that they have done. Yes. It's kind of so you some heuristics for position has been written from there. You can get the hip angle, but the more logical thing to do probably would have been to just get the hip angle directly based on some of. But anyway, this is somebody else's model. Excellent. They just wanted to calculate how far the foot should be placed. Sir, if you want to proper forward, you make the stance. From there, directly, what you will get will be gamma actually. Yes, sir. Like what they wanted to calculate was gamma, but they directly got a gamma. You want to hold this here, but then you are holding this here, and then you say that this here, this here, this here. I think something like that. Yes, sir. So for the hopping control, what they used in their leg was a pneumatic cylinder. During the swing phase, when the robot was in air, they set at a particular pressure that corresponded to a particular stiffness in that cylinder that decided the height at which it will hop. So this approach for move, they extended this approach for multiple. And this diagram again, I think. Yes,
they would have drawn that themselves. If there is a pneumatic cylinder that is there, technically that blue line should not be one single line. It should be two bodies. Can have relative motion in between, which is what will give rise to this spinning motion.
Yes,
there is a flexibility that is there in that.
Yes, this simulation, I have done this simulation and I have placed the pneumatic cylinder that they were using to simulate a spring by action of the spring.
The length of your simulation. The length is simply that is placing.
Right, so that is the schematic which you have drawn.
Not one rigid body. Either you say that this is one flexible body which can change in length, or you say that there are two bodies which have a prismatic joint in between. It's like a shock absorber.
Yes.
But activated.
Yes, so for simulation, like it should be shown like that, but the idea is the same. That they wanted a spring at the leg.
No, what he is saying is that you should have drawn the figure correctly.
Yeah.
Kinematic diagram. Anyway, you will be working on this, so at some point of time you will have to be. It's better that you try to make figures which are like theoretically synthetic figures. So, for example, in that you have 10 gamma and phi, but the length of that is also another variable. So that is what you are controlling using the pneumatic cylinder.
Yeah.
That is what is giving rise to. But in these equations, I don't see that anywhere.
So what?
Okay. That basically comes plays its role in the hopping control.
Yes.
Because you have not written any equations for the hopping control, that is why it is not appearing.
Yes.
Technically, it should be appearing somewhere.
So should I? So they use this single-legged control scheme, and they extend it for multiple legs by proposing a concept.
What is body attitude in your can you just go?
Sir, this is
the
a
body attitude and then hopping control. Hopping control is basically the height of that, and that is what should be the attitude of the body also. Why are there two different terminologies?
So why should be the attitude of the body? So by body attitude, they want to say the orientation of the body.
Oh, so angle phi.
The angle phi, they want to. This phi they control in the third part of their controller.
Okay, sir. Body attitude. Attitude typically is a terminology which is used for height.
So that's attitude, sir.
Attitude.
Attitude, spacecraft attitude means the
General orientation. Okay. So this single-legged.
Attitude.
So this single-legged control scheme that they developed in one of their previous works, they extended it to be used in case of multiple-legged robots, and to do that, they proposed a concept called the concept of virtual legs. Yes, sir.
Locomotion using single leg.
Yes, sir. That is for single leg. What I have shown in the previous slide, they extended that single-legged algorithm, that single-legged controller, to work for cases with multiple legs, for robots with multiple legs. And how they achieve that is through defining a set of virtual legs whenever there are multiple legs. So, for example, if we take a particular gate called trot, so in trot gate, the diagonal legs of a quadruped robot, they always move in unison. So these legs that are acting in unison, they are called to be functionally equivalent to represent a single leg at the center of the robot. So now what they are essentially trying to do is they are trying to reduce the model of the robot from a quadruped to biped, and then since biped has two legs, they use a finite machine-based switching logic that they have given in their paper. So what they do is, whenever one leg is in contact, they use their three-part control scheme for that particular leg, and whenever the other leg comes in contact, they switch the controller for that other leg, for the other virtual leg.
No, but the other leg can swing independently and keep the foot wherever you want. Right?
Yes.
Because whichever leg is in sync phase, I do not control it independently.
So, sir,
because
this is not like they whichever leg is in swing phase, we treat it with the what they did was
You can swing it more so that it can increase the step length.
yes. So what I mean when they switch the controllers is whichever leg is in swing, they control the foot placement of that particular leg for next step, and the foot that is in stance, that is in touch with the ground, its dynamics is it can be approximated with the inverted pendulum dynamics when it is in stance. Okay, so
Control is actually on the swing.
on swing leg, yes. So yeah,
Independently or independently, but in some sense that is kind of constrained. In the sense that because when all of them has to be continuously in the swing phase, that means the height, you cannot arbitrarily go anywhere.
yes.
Because the moment it goes beyond that thing, that will lose for it.
Yes, sir. So this was not the best controller. Even they have mentioned many shortcomings of this controller. But what?
Controller is basically unconstrained. There is no constraint on what is the top height that you can achieve.
Yes, sir.
And the moment that there is second leg which has to be in the stance,
Yes.
there are constraints on that.
Yes.
Or there is a coordination that is required between the forward motion and the hopping.
Yeah. So the coordination is required, but they do not use the coordination here, and they show that even without the coordination, it is able to track the velocity. Not exactly, but within certain acceptable error bounds.
But in human walking,
Mhm.
so the hopping is basically because of the heel strike and stiffness of the foot, or what is the idea behind using the hopping kind of mechanism?
So they don't want it to simulate human walking using this controller. They just wanted to simulate any kind of running using this controller. And also, we can see, given the type of control scheme, any robot cannot move forward without jumping, without its legs leaving the ground. So that is a limitation of this controller. It cannot, and also it was not. They did not propose it for walking, but for running scenarios where the robot will leave the ground.
Both will be. So you have
But when
possibility
you
of.
both leave, then you have a problem. You cannot switch, right? Because both are on kind of on swing phase. When you actually run,
Hmm.
you jump.
Yes.
When you jump,
Yes.
there is no leg which is on ground. So
Yes.
both of them are on kind of swing phase,
Yes.
right? So then this single leg control will fail. Because you want to control both the legs. Right?
Yes, sir. So what I'm saying is I'm mixing up the control strategies they use for different kind of gaits. For example, for trotting, what I said before, that one leg is in stance and another is in swing, and they use the control on the swing leg. But for gaits like bounding gaits, they have to jump because these gaits include full flight phases of the robot. So they use these different combinations of the same control algorithm or the set of legs that they define at different places. So the key takeaways from this paper were that even simple heuristics can be used to control legged robots for basic symmetric gaits. So this paper is actually what many people interested in researching on legged robots. Also, many researchers try to look at the biology of walking and how does animal how does the controller work for animals. Okay. So that is where the idea of central time generators came into picture. So in this video, what the researchers did was they severed the spine of this cat such that the brain of the cat cannot send any signals to the legs of the cat, and they hung the cat on a treadmill such that its legs were just touching the treadmill. And by modulating the speed of the treadmill, they were able to see the legs reacted, the joints of the cat, they reacted to the sensory input without getting any signal from the brain. So this was an experimental verification of a bunch of neurons or a group of neurons being present in all the joints of the mammals that give reflex actions at the joint level without the brain being involved.
But it could be through the spinal cord, like our body also.
So
There are
this
some signals which are controlled by the brain, some which are relaxation which is controlled by the spinal cord.
yeah, so sir, this some are controlled by the spinal cord. So this is what they're saying, that reflex sections are also they also happen through a bunch of neurons either in the spine or in joints.
Yes, be sure that they are in the joint. That is what they get severe spine. Joint to ऊपर से करते हैं, brain is spine में है, but spine का signal जाके आ रहा है कि नहीं, you don't know.
So what is saying is that
the body,
spine is
human body has been kind of established. That okay, brain है and the reflex action is through the spinal cord. It is not at the joint. Human anatomy is that reflex action, spine is involved.
So you mean to say like only the spine is broken but the cord is still there?
Yes.
Or the cord is also chopped.
So like
Brain to
spine connection has been chopped, but the spine to joint like connection has not been chopped. But what sir is saying, the reflex section happens because the spine is giving the signal that is required.
That is how the reflex action typically, that is the understanding of the reflex action in human body.
Yes, sir. So when we say the joint level reflex section, the controllers need not be present exactly at the joints of the robot, but whatever neurons control whatever neurons send the signal to the joint, they need not get any signal from the brain. Okay, so what is it?
Reflex action, no planning.
Yes, there is no planning. So this. So,
Nimesh, you may like to Nimesh.
But they are being fired. Over a period of time, even without a control moving from the brain, because they have been firing in that pattern, there is a kind of feedback that they are getting from the sensors, they continue to do that. So it's a network.
Essentially encode the signal that they got and more within their awareness, their own awareness.
The muscle can remember that how it has to do.
So we can say dynamic fluid series approximation, because this dynamic fluid series approximation is a term that we use for harmonic oscillators that we will discuss in the next slide. And one more thing is that this learning
Could be any melodic solution, not necessarily harmonic oscillator.
Yes, but this term, the dynamic Fourier series approximation, it is mostly used for harmonic oscillators. When we use harmonic oscillators.
For periodic signals, not for harmonic. Harmonic means that it is sine or cosine.
Yes, sir. So
Only for sine cosine, there is no Fourier series. No? If it is only one sine or one cosine, Fourier series will use a periodic series.
This is not a single oscillator. We use multiple oscillators within a single CPG that approximate the different frequency components of the input signal.
Each one having a different frequency.
Yes. So I'll discuss that on the next slide when I talk about the implementation, how researchers implement it. So one of the major advantages of this technique is that there is no need for optimization to learn or encode the trajectories. And also, the parameters of the CPG, they can be modulated online to generate new trajectories out of the ones that it has learned or encoded before. So it can just, if the user or the researcher modulates the parameters of the CPG, they are able to generate new gates without any high-level planning involved. And also the sensor feedback can be integrated with the CPGs using something called the feedback pathways that we'll discuss. And also, this is a typical CPG-based control architecture where the reference signal is attached by a switch to the controller, joint controller, and whenever the switch is closed, the CPG network it encodes the reference signal, okay, and it sends its output to the whatever low-level controller that the joint is using. And whenever the switch is opened, even then the CPG continues to give the same output that it was giving when it had the reference signal. So, so the reference signal is any periodic signal that we want the CPG to track or to approximate. So let us say if we are talking about joints of this guy, so whatever this joint trajectory should track to move on this treadmill is the signal that you want to input. So coming on the implementation CPG, so one of the most oscillators as a simulated neuron for CPGs is the Hop oscillator, and the Hop oscillator, it has been modified to be used as a neuron in CPG with some adaptive rules and a coupling scheme called the promoter coupling scheme to maintain the phase difference between multiple oscillators, because now this is a diagrammatic representation of a CPG. There are multiple neurons involved in a CPG, and each of the neuron, it converges the frequency of each of the neuron, it converges to the frequency in the input signal nearest to its own frequency. So if there are 6 frequency components in the teaching signal or the input signal, and I have 6 neurons whose frequencies are near to the frequencies of the input signal, they will converge exactly the frequencies and the amplitude. They will converge exactly to the frequencies and amplitude of those particular harmonic components of the input signal. So
what is RI over here? RI is square root of xi square plus I.
Yes, I is the radius in phase space. Under root of xi square plus I. So that is where the non-linearity in this oscillator comes. No, so, other than Hop oscillator, other oscillators have also been proposed. One of which is the adaptive Vanderpool oscillator, and then there are Rayleigh oscillators, adaptive Rayleigh, adaptive Fitzel-Nagumo oscillator, and adaptive Rossler-Strange oscillator. So all of these have been proposed, not tested or verified to be working for any robot. And one of these papers that I have referred below, they used the Hop oscillator with this particular coupling scheme, the promoter coupling scheme, as a joint controller for a biped robot with 10 different joints. Okay, so for every joint, they define a CPG and they further connected these CPGs through what they call chain coupling. Okay, so the chain coupling within these different CPGs was introduced to maintain phase differences between these particular joints. That should always be there. And other than chain coupling, they also introduced one way to integrate the sensor with the sensor feedback to maintain stability in CPG-based architecture, and that was through introducing feedback pathways to some selected CPG. So, if for any particular whatever sensor signal sensors they get, if they want some particular joints, say hip and the leg joints or the ankle joints to move, then only for the equations of those CPGs, they will augment those equations with these feedback pathways that they define. Basically, they will augment them with the sensory feedback. So,
GK are positive gains or negative gains? GK,
yes.
These are like positive or negative?
So it is a positive because it is treated as a perturbation to the limit cycle of the oscillator.
It is always positive. Then
It is always positive.
there might be issues with the stability of the system.
No, what they are doing is they are trying to perturb the oscillator along the radius of the limit cycle. That is why they are projected on both. We can see that it comes in the both x and the y equations. And any perturbation that is perpendicular to the limit cycle, it damps out in the long run.
When perpendicular would mean that it has to have, depending on where it is in the phase. Theta is representing the phase.
So phi is representing the instantaneous phase of the oscillator, and theta it represents the
What is tan inverse of phi? Yes.
hmm?
There has to be a tan inverse of
Yeah,
phi.
that is fine. That is fine.
That is phi.
Yes.
Then for the perturbation to be normal to it, there should be dependence on phi. No? That by xi by
So
ri.
this x by ri is cos phi, and this y by ri is sin phi.
In the convention, the normal one has to be the opposite.
Hmm?
Normal has to be orthogonal. What is the
X and Y both are being perturbed, right, by the same GK.
That is by the same thing. So should I use the board?
You are saying that basically what is trying to say that this perturbation is along the normal. Is only the coordinates. Xi, yi will represent the normal.
Yes. So
Yes.
this is
Okay.
okay.
If the origin is at the center. Okay. Yeah.
So
ठीक है. Then y by ri just to get a sense of the angle.
listen, this is the complete perturbation is g of k, and I'm projecting this perturbation along the radius. And when the components in the xy plane, they come like this. So the key takeaways from this concept, the CPG concept, is that the internal structure of the centripetal generators, it can be exploited to get inherently stable motions for naked robots, with the possibility of online modification of motion by changing the parameters on the. So these CPGs have inherent stability, but now I will discuss some stability of these robots that are not inherent to the system, but that is defined for the controller to be able to exploit them. And the one that I'm going to discuss is the concept of capture point and capture region. So capture point for any linear inverted pendulum or any robot is the point at on which it should step for the robot to come to a complete stop. if it is going with the velocity. In the image here, I have used two different representations. One is for the head robot, and one is the contact polygon of a quadruped robot. So, for humanoid robot, so a group of capture points is for the capturing, and these green regions in these images are capture regions. This particular humanoid robot, and whenever the capture region, the feet of the robot is in the capture region, the robot is stable, and it does not have to take any steps, it can just stay there. Whenever
these are all points where if that is the point where the next contact of the happens, then
it will
there is
come to a complete
stability,
stop.
there is balance.
Yes, there is balance, it will just
It will not come
stop. It will not happen.
Coming to stop, though, you can make it stop anywhere. But the point is that it stops such that it is statically balanced. That is what you want to say.
Yes.
Otherwise,
The velocity is zero.
what velocity will be? Velocity can be perfectly zero by if I just have this point here and next point somewhere else.
Yes, I mean it should be zero and it should remain zero. It should be statically stable in that particular.
Stability is very important the capture point.
Yes. So, and if this capture point, so whenever it is inside the contact polygon, it is stable. Whenever it is outside the contact polygon, then the robot needs to take a step to get this capture point inside the contact polygon. And how they define this capture point? They define something called a pendulum, a orbital energy of a linear vector pendulum. And whenever this energy is positive, it means that a linear inverted pendulum is going to tip forward. Whenever it is negative, it will reverse its direction. It will stop and reverse its direction. And whenever it is zero, is the case when the center of mass comes to rest. So the third case is what gives us the expression for capture point. And for any type of robot, what we want to achieve is we want to take the center of pressure of the robot to the capture point, to the coordinates of the capture point. And this condition is what maintains, what ensures the stability of the robot. That the capture point should be at the capture, center of pressure should be at the capture point.
The center of pressure is something that is defined for an individual foot, not for the whole.
It's a totally
For one foot.
it is defined when there is a contact polygon, center of pressure. So, for example, in the case of quadruped, if there are forces F1, F2, F3, and F4 acting on 4 different feet of the robot, then the center of pressure is defined as the weighted sum of the position of the feet. The weights are the forces at the particular feet normalized by the total force. So that
Generally, even when there is one foot in contact, for that foot contact itself there is a center of pressure.
yes, sir, there is because there are multiple
That is
contacts.
function of the- And the people is actually representing that center of pressure for that field.
Humanoid has got
Yes, sir.
both with some length. What is saying that between the ground and the foot, there is a pressure distribution. Right? So there is one point where you can assemble all the pressure and show it to as resultant.
Yes.
But this is talking about when the
Other
both
quadruped.
foot are, no, even in the human, both foot are on the ground. Then you construct a polygon and make sure that your PG or your thing passes through that polygon, right?
Yes, sir.
So
So
if you have P1, P2, P3, P4 that you are talking about,
yes.
these are the individual center of pressures of that particular field which is in contact.
So, sir, what I have
One is not so.
what I have
Is mind, those are the point
sir,
for
for quadrupeds there are point feet. So there is no polygon for every feet. For the
There is a
human
contact point, there is one contact.
no, sir, we take the ideal case that the contact is the point contact, and then we make a contact polygon like this. Even in the case of bipeds or we don't. So even if single leg is in contact or both the feet are in contact, what the center of pressure should lie in convex hull of all the contact points, not just a single field, for the robot to remain stable.
There are during different phases of the game, that center of pressure point that keeps changing.
Yes, sir, it keeps changing, but whenever there is a dual support phase, the center of pressure it lies inside the total support polygon. And there are no
one phase different
yes,
like this inside
whenever
there is no static equilibrium there.
When you are transitioning, there is a
Separate.
you see, when you are getting in the swing, from the swing phase to the stance phase,
yes, sir.
that time the center of pressure is towards the back of your AP. Then when it goes into the full stance phase, that is where then it is get distributed comes to the center.
Yes, sir.
Then when you are doing the transition from the stance phase to the swing phase,
There are two different things that are happening. What you are talking about is what happens when you actually respond this thing and slowly the contact point is happening. Right? Now you consider a simple model where you have this real humanoid would have flat kind of foot. Is on ground, it is more like a moment it comes here, I don't want the weight, the resultant force that is acting beyond the control polygon, then it will topple and bottom.
Yes.
So there is a momentary static stability that is needed.
even there, even if you have a flat foot, the distribution network is uniform. The contact point is not just at the center. No, center of pressure could be different. In fact, there are these people who work this, so there is this ground force reaction constant that has to be put to ensure that prosthetic people do it. So one of the students did some work on that.
Then how the center of pressure is defined in these kind of robots is there is only one center of pressure for one robot, and that center of pressure is defined by the complete contact polygon at any instant. If it is in the single support phase, then the center of pressure should lie inside the center of pressure of the single group that is in contact. But when it is in double support phase, it should lie inside the complete contact polygon and not just a single. And there will only be one COP for the whole body. So
During motion, the COP position keeps changing. That is one thing. And if people have not really considered it when doing all of this, then that is something that might be pushed into focus on.
Everything is in one plane. It's easy to say that there is just one single COP for the whole robot. But if in one different, then what he says is good COP is important because that is the physical point of
Human terrain will become very important.
where the reaction will actually pass through. But
Yes,
this, there are 2 feet. There is not permitting. This is a kind of virtual point where the total ground reaction force will.
And it is probably a good approximation to consider it to be a constant, but maybe things will mature to a level where
so I think that is, for an LIPM that is augmented with a sliding that can generate toss on the mass of the robot at the top of the LIPM. We have a complete range of these capture points, and this range, these multiple capture points, is what we call a capture region for LIPM. And for this particular robot, we define a region in both the x and y direction of the plane. That is why it looks almost like an ellipse or an oval in the case of the humanoid robot. So, the major takeaways from this concept is that a point can be defined for stable stepping in case of legged robots, and also the expression of this capture point it can be modified to maintain a target velocity.
what exactly is Z0 over here in your all the expressions?
So Z0 is the height of the linear inverted pendulum that
have drawn a picture of it. This analysis was entered only over a pendulum. It's horizontal.
yes, sir. So
Anyway, during the stance phase, actually the leg can be modeled as a single rigid link which is like that.
Any degree of freedom is kind of low.
Lock. That is why while doing the motion planning for the thing, there is another thing that is where I was thinking from that the ground reaction force should always be presenting such a moment that the knee is always down, should not roll down. So that is why, and when doing that, the context, the center of pressure is changing. That has to be taken.
Actual strong ankle.
So basically, you want that during the standstill, it should not happen that the knee was locked, but the ground forces are producing a moment such that it actually starts rotating in the other direction. You should always remember that. Good.
So this particular concept, it is. So there is so this concept of capture point is also used to define stability margins, where the stability margin is defined as the distance of the particular center of pressure of the rod from the closest edge of the contact polygon, and it was extended by these guys in this paper, by these authors in this publication, where they defined stability margin criteria for dynamic stability on uneven terrains. So whatever was done earlier when defining stability margins for plain terrains or flat terrains. So what they did was they used the instantaneous capture point that the authors in the previous paper had defined, and they defined a feasible region for the robot using an algorithm called intervention prediction algorithm, and they used the distance of this instantaneous capture point from the nearest edge of this feasible region, and they defined this distance, this minimum distance, as the analytic stability margin for dynamic stability uneven terrains. And also to speed this algorithm up, they used neural networks for fast estimation, where they would give this whole parameter vector lambda that was used for calculating a feasible region, and this lambda consists of the gravity vector and the center of mass, velocity center of mass, acceleration, and angular accelerations, the external forces, feet position, feet forces, and the normals, the contact normals at the point of contact. So they used this lambda as the input to the neural network, and they used this analytic expression as the teaching or the ground truth, and they trained a model to speed up the estimation of the margin. Yeah. Yes.
Is nearest distance is computed by extending the edges of the separate polygon.
No, so it is not. In this case, it looks like a support polygon, but what they define is not a support polygon. They define a feasible region where the robot can be, and it includes the kinetic parameters of the robot also. That can the robot reach there?
This analytic stability.
Yes. Edges of the feasible region. Yes, it is not the contact polygon. It is not the contact polygon. It is just a region where the robot can reach, and the feasible region is defined for the uneven terrain. Instantaneous center of pressure. So, not center of pressure. Instantaneous capture point. So, sir, support polygon can be defined, but they are not, the stability margin is not really defined.
Feasible region is subset of the support polygon.
No, the support polygon is a subset of the feasible region.
What he's trying to say
Then you need to have an intersection of the feasible polygon and the support polygon, right? No?
Why, sir?
Because if you go outside the support polygon,
Yes.
you lose the stability.
They are not defining the exact stability, they are defining the margin for the stability. And now what they want to do is they want to keep the center of pressure or any point of force, either the projection center of gravity and capture point in this case, in the region where it is a high stability margin. And this high stability margin region is a subset, uh, of the contact polygon, or it can represent a contact polygon.
Yeah, and it's very interesting to know how exactly it is related to the portfolio.
So, sir,
Because your previous slides was talking about that your what you call capture point.
yes,
That should always be within the portfolio. And
Yes.
your feasible region actually talks about the kinematic constraint of whether that is possible or not. But finally, everything should be within.
yes, sir, for the motion to be
And
stable.
if it is, for example, the stability margin may also mean if it is very much in the interior of the polygon,
Yes,
then it is very stable, right?
yes, sir,
As it goes towards the boundary of the polygon,
yes,
the stability is weakens.
yes.
I want to understand everything related to stability polygon. My thought process is right.
Yeah. So, sir, what they wanted to do was they wanted to define a new way to define stability margin. There are like the existing ways. They include the distance of the say, point of interest, be it the projection of the center of gravity, or the center of pressure, or the capture point with the contact polygon. But they expanded this region or the polygon from which we are taking the distance to be a feasible region and not the contact polygon.
No, no, my question is still how this is in relationship to the polygon. Can it be larger than that, or can it be totally different, or it is a subset of this?
So if
Or
we
is it an intersection of
Yes,
this?
sir, if we see in the diagram below, this colored patch is the feasible region for this robot.
Okay.
Okay, now we can see that it does come outside the contact polygon of the robot.
That is fine.
Yes. So the contact polygon is a subset of this feasible region.
May not also be because some of the region within the contact polygon it may not be able to move, right? It may not be mathematically possible to go there. So what I'm trying to say is the intersection of these two is of interest. I don't know if I can.
Yes, sir. For further analysis, that which region to actually choose, then the intersection of both of these can be of interest. But if we can define a region where it is high probability that it will be stable, that they can even define without talking about the contact polygon.
I don't think. Then you will have to go about the definition of the stability margin and how they have actually derived that and how symbols mean inside.
Okay.
Of course, you don't have time for that, right?
So I can explain.
Yeah, briefly.
Yeah. So what they do is they use this incremental projection to calculate the feasible region. So what they do when they calculate the feasible region, they calculate the edges of the feasible region, and then they calculate the normals at the feasible region. So this N is a matrix that has the normals of the feasible region. So now this is just they want to calculate the distance between this point. They want to find the minimum distance of the ICD with all the edges. And they choose the distance that is minimum as the stability margin.
I need some time.
Sorry, we can after this we can discuss.
Where did the lambda go? Lambda is just giving that hyper.
Yes, the lambda is being used for the feasible region.
No, you use ICP.
Yes.
And once you have ICP, then you come to compute MA.
Yes.
But you need N's.
We need n's and we use
For N's, you will need lambda.
yes, because n is a matrix of the normal vectors of the edges of the feasible region. So, yeah. So they used this analytical stability margin that they defined to train a neural network model to speed up the estimation process. And so, yeah. So these were some of the methods to quantize stability of legged robots. Now, using these stability criteria and uh, models of the robots or the system.
What does stability mean?
Hmm?
What does stability mean here?
So for capture point, stability means like there is static stability and dynamic stability. For dynamic stability, there is one concept called the concept of capture point, where we are confident that if the robot steps at the capture point, then it will be stable. And stable means it will not fall down.
Dynamics is taken into account, not the static.
Yeah. So for this, for calculation of this feasible region, the
No, no, only to this. Whenever we use certain words here,
yes.
so I want to know what you mean by stability, what you mean by stability matching.
So
We will go back to their equations.
yeah.
Okay,
Yes.
I want to understand stability.
Mhm.
When you use the word stable,
Yes.
what do you mean by that?
So I mean that
Or
the
in their context, of course, not you are talking about what they are.
yes. So what they define a motion to be stable is a motion in which the robot first of all does not fall down, and the errors in tracking they do not grow very large.
No, those two are totally different.
Totally different. Yes.
What we are actually talking about here. Is it about the synthesis of the gate so that entire process it won't fall down? Do you mean stability by that? Or do you mean by the from the controller perspective the closed dynamic system? So those are totally two different concepts.
Yes. So not the second.
Because if the controller is also not stable, then it's a will fall.
Yes,
That
sir.
is
That is
to that.
yes. But this stability margin, they went on to use this stability margin, this particular stability margin, in a text optimization based approach that they verified, that they implemented in the paper, and they generated motions that were stable, when the robot did not fall down.
So the controller is part of the stability generation of the trajectory.
No, it's a controller.
Trajectory generation is also your problem, and the controller also is your problem. Both of them are integrated into one.
No, they are different. So trajectory.
Trajectory generation.
So only for trajectory generation they will be using this.
Okay.
Okay, and similar trajectory optimization based approaches have been used by different people. And one of these approaches include what they call phase-based end effector parameterization. So what does phase-based end effector parameter? So in this paper, they chose a contact model. Contact model. By contact model, the authors mean how the feet come in contact and how do the timings change when it is in contact. So they uh, treat every feet individually, they treat every leg individually, and for all the feet, they define times at which it will be in swing and it will be in stance, and they keep these times as variables for the trajectory optimization.
And all your leg models are single.
Yeah, so this particular image here is for a two-legged robot.
Links in the individual leg.
Yes.
Does it have a knee joint or it is more like a?
So it has a knee joint. It has a knee joint.
It's a double pendulum.
Yes, at least a double pendulum with an abduction joint. So they define these phases for the feet of the robot, where every individual feet, we can say that.
There is no exclusive.
Hmm?
You have the foot also, or you consider amputated?
No, we consider it to be a point contact, a feet that makes a point contact. There is no extended.
That is.
Yeah, that is not there. So they define these timings at which the feet comes in contact with the ground and when it leaves the contact as variables. And what the idea is, if they treat all the legs as different, if they treat all the legs independently, then if the optimizer changes these times for one of the legs, it gives rise to a completely new gate that is more suitable for the given whatever the task that they want to achieve. And this is the example for a two-legged robot in which if the first leg, the timings for the first leg did not change, but the timings for the second leg did change, then we can see that it has flight phases also in its gait, and it has longer dual support phase. The L here stands for when the left foot is in contact, R here stands for when the right foot is in contact, F stands for full flight phases.
Walking on flat ground, right?
Yes, this
Then what
is.
is the asymmetric kind of
So, sir, this is for a four-legged robot. This example, this whole approach is for four-legged. This example is for a two-legged robot, where we just want to show that by changing the parameters, these timings, phase timings of one of the legs, a completely new gait can emerge. So this extends to a four-legged robot.
I think then it is advisable that you make that diagram for quadruped.
No, this is
Sir,
to just explain
it is just
that,
to
even if one leg
explain the timings.
changes, it is something different.
To avoid confusion. For you it is like that.
Mhm.
I think he was confused. No.
Not exactly, I was trying to understand.
So is this?
I got it.
Is,
I got it.
okay. So the idea is that by changing these phase durations and by letting the solver change these automatically, new gates can emerge that are more suitable for your given task. And in this,
Has it been observed in,
yes, in
a non-symmetric kind of gait pattern?
Yes,
or
yes.
walking on
Yes,
flat?
sir. Not exactly when walking on flat, but
Unsymmetric means how will you define it?
See, for example, here what is happening, typically you keep this leg and if there is a,
So first and former legs are in contact.
how much time I want to keep this foot on ground? It's same for other foot, right? I will not keep this for long.
No,
Then it will be like single leg walking kind of thing, limped kind of walking.
suppose you want to change the gait of the flight.
No. What I'm trying to say is normal walking, it will be symmetrical for the both of you. At that one moment you might start the increased right leg, that is different. But in quadruple case, it doesn't make a difference. At least in bipedal motion, I don't see any advantage. If you are walking on a uneven terrain, then it makes sense because one foot may be at a different height and things like that, or including its ground condition could be different, so that is fine. Because many people do walk. Sometimes, if you are comfortable writing with right hand, we will typically put more effort on one leg. That happens actually.
okay.
But is it optimal from this sense?
So, sir, this may.
No, this I understand.
Yeah, no,
This
not sir,
portion I
this,
understand,
this,
but
the approach here.
into the four-legged.
Yes, so for four-legged, they tested this approach even for uneven terrains. There they saw that these different timings do emerge, and for flat terrains, these different timings emerge when they made the robot jump for a distance. So to set up the jump, the robot actually modulated its gait so that it can cross whatever length they specified that it should cross. So in that case, even for a flat terrain, the robot did modulate its gait to prepare itself for the jump. So even for flat, so in this whole trajectory optimization formulation, they did not use in this particular paper. They did not use any cost function. It was completely to find a feasible solution given the kinematic constraints where the feet were where the uh, constraints or the feet position were constrained to be inside a cuboid that was a subset of the workspace or the feet, and the size of the feet was taken as 2b, a cuboid of size 2b. And then for the dynamic model constraint, they use SRBD based model. So SRBD is a single rigid dynamics model where for the inertia of the robot, they keep it the same throughout. So they take the inertia of the robot in the nominal position at the start position and they keep it the same throughout, and this assumption is valid only for cases when the inertia of the legs, the momentum of the legs is negligible. Now it can happen in one of the two ways. One is if the legs have negligible mass. Second is if the legs are moving very slowly. So they use an SRBD model for represent the dynamics of the system, and they use then the parent height constraints that the feet of the z coordinate of the position of the feet should be equal to the height at that particular position, height of the ground at that particular position. And then there was transverse constraint that the robot's feet should only push into the ground. All the forces should be positive and it should not pull into the ground. Then there are friction pyramid constraints. They did not use friction cone constraint. They used an approximation of the friction cone that is known as the friction pyramid constraint. And for every foot, okay, they define the full feet of the every trajectory when the feet was moving. So whenever any foot was in swing, they defined its motion using a parameterized cubic polynomial. And whenever it was in stance, any feet was in stance, its position was defined by a constant function to enforce that any feet in contact should not slip. Any feet in stance should not slip. And similarly for the contact forces, they used identical zero, a constant value, whenever the feet was in swing. And for when it was in stance, they used cubic polynomials to represent the contact forces.
Why,
Yeah.
why that variation in that force there? Why cubic polynomial in stance space?
So they wanted now they did not specify it completely.
So what are those points and slopes that you are showing there?
Yeah, so sir, they are just they used three different cubic polynomials.
Okay. Those are the points and the slopes were specified to be
A C1 continuity at every point when they are.
But how did they select those points?
Hmm?
How did they select those points?
Yeah, so sir, these points are not fixed, but what they wanted to specify is that these curves can change their shape to better fit the final force profile that will be there. So this force profile finally will be different for any given task. And also, so here also in the position they use three different cubic polynomials with C1 continuity at their ends. And they specify maximum number of steps for every leg. So why they specify the maximum number of steps is because for every leg they had already established that it will be either in swing and stance and it will be alternating. So if for any specified gate it has to take lesser number of steps, it can just make that phase durations of any swing or stance phase to be zero. So essentially, it can reduce its number of steps by reducing the time for that particular step and making it zero. And the time for the SL contact, where they define whether it is in any foot is in contact or not, is defined by these phase durations that they have defined, because as already established, any single feet will alternate between stance and swing. And the last constraint, another constraint is the total time constraint. where for every feet, all the phase durations should add up to the total time of the motion. So the key takeaways from this paper, so they solve this problem without a cost function, given these variables to generate motions. And the key takeaways are that SRBT model, an approximate model, can be used to generate motion for quadruped robot, and phase-based parameterization of feed can give rise to new undefined gates that are better suited for the given task. So the next paper also extends the trajectory optimization.
Do you consider the weight and the whole body weight and movement, where that is the contextual?
So, yeah.
And it's CG or where the force is acting, all those things would come through that. No, the net force exerted by the upper body on the
Yes,
that is what is important. Right?
yes, sir, that is the
Okay.
gravitational force.
Position is
So this R is the position of the center of mass of the body, and P is the position of the feet,
okay.
and
Is the
F is the contact force,
reaction.
force at that particular at ith feet. So this used a particular model, and this used SRBT model with phase-based parameterization. Another approach was that the same authors from the previous paper they proposed was to represent the full body dynamics of a quadruped by using as a switching dynamic system, where the dynamics of the system it changes after a certain time. Okay, so what they so they they wrote down the equations of the full body equations of the quadruped robot as a switching system model, where the dynamics change after a certain given time. And once they had established the equation of motion as a switching system, they again proposed that a switching system, the optimal control problem for any switching system, can be represented by this, where the cost function includes the terminal cost and the running cost within a particular phase, and we add up all these we add up these costs for all the different dynamics that are happening that are subject to the general system dynamics, initial conditions, and the state and spin and the control into two different optimization problems, where they first optimize over the switching times by taking the control as a given parameter, as a given quantity, and then once they have optimized for SI, that is the parameters, they take that as given and they optimize for the control, and they keep doing this until both of these converge. So it is an alternating optimization procedure that they follow. And so for the top level optimization, to optimize for the switching times, they use a gradient descent based approach. And for the bottom level optimization,
Usually for the gate or trajectory generation, not control, right?
not control, only for trajectory generation. And
So it is done offline.
it is done offline, but they also claim that this particular implementation that they've written, it can also run online. It can,
But there is an iteration between.
Yes, sir. Like they claim that all of that iteration can happen within 100 milliseconds.
But then it is hardware restricted, right?
Yes.
You must have spelled out hardware. Maybe going forward it will be faster.
Yes, sir. They use pretty powerful computers on their robots. They use Intel. So for bottom level optimization, they proposed a constrained SLQ algorithm where they chose a quadratic approximation of the cost function, linearized system dynamics and constraints. So using both of these, they used generalized constraint LQR formulation to finally get the net neural.
System dynamics.
Yeah, system dynamics and constraints. About nominal trajectories. So about the current trajectory that is there, not the complete
Every point.
at each. So yeah, at each and every point. Yes. So now what I have already iterated that they alternate between these two optimizations to finally reach the solution. So major takeaways from this paper were that Leggett system dynamics can be represented as switching system dynamics. Also, trajectory optimization for switching system poses a parametric sequential optimization problem where we have to optimize for both parameters and some sequences that we have defined. And the parametric sequential problem can be solved using the multi-level optimization approach that is proposed by Zuen and Saklis. So, building on this paper, another paper was introduced where they used multiple passes, specifically 2 passes, to generate highly agile motions. For example, performing a barrel roll or performing a 3D diagonal jump. So for these kind of motions, what they established was and what they found was that
Barrel roll is forward direction or sideways?
sideways. Barrel roll is sideways. So what they found out was that if they used only approximate dynamics, the SRBD dynamics that many people were using.
Those kind of motions,
Yes.
we find them prominently in biological world.
No. But
One way I look at it is,
hmm?
you are going back to the biological world.
Yes.
You get a solution for the problem.
Yes.
Right? So your ideal purpose is to make a robot
Hmm.
go from one point to another point.
Hmm.
And most of the animals or certain specific animal is good in certain specific terrain, that is fine.
Hmm.
Right? So you want to be, if you can actually find out why an animal does certain things,
Hmm.
and if you can actually generate those kind of solutions using these kind of approaches and make your robot perform the task, that is what is our purpose. What I see as an alternative approach is purely academic or purely not even academic. Like you want to show something fancy. What is the use of those movements from any perspective? See, neither from a science perspective, I am not getting any understanding out of it.
Hmm.
From engineering perspective, I am not getting solving any task in a better way out of it.
Hmm.
For example, even when you want to go on this hilly terrain, you will go in a horse, right?
Hmm.
The horse is capable of. So I have not seen any animal. What is the motivation for all this complicated game? That is my question.
So this is to establish that what kind of models we should use if we want to generate dynamic motions that are highly agile. Now, the barrel roll does not. Now, no animal does a barrel roll, but a barrel roll is a highly dynamic and a highly agile motion. And if an approach can generate and track that kind of motion, it can also be used. The same approach can also be used to generate different agile motions that the animals actually do. Like
Why
whenever
don't you focus directly on what we want instead of creating certain artificial? For example, if you come to aerobics kind of thing,
hmm.
okay. For For example, I mean, if I can go back to whenever these kind of things are there, I have seen one video recently, which most of you might have seen. It was related to a football, a link to how a lion actually jumped and caught a piece of meat which was thrown.
I am not.
Okay. So there is a very complicated kind of motion which is not normal here. So the idea for the reason some of these people work on this problem to demonstrate what all they can do.
Yes. So, sir, what they established was that to execute these highly dynamic motions, you cannot do it using an approximate model. If you use an approximate model to get the contact timings and an initial guess for the reference trajectory, and then you again use that initial guess with the same contact timings to tune this trajectory to the full body dynamics of the particular robot, then it is able to achieve these dynamic motions that we wanted to have. And one of the motions that they achieved happened to be a barrel roll. But
If you are
yes,
no, what I'm saying is that if you are able to do this barrel roll successfully, will you be able to learn about push recovery? That if the robot is hit from the side, it falls, then can make a roll and stand up or something.
so it will not be able to learn that kind of thing from this. What they're trying to do here is they're trying to generate trajectories that if we make the robot track, it will perform that particular motion.
What is his objection that why fancy
Yes, sir.
when it is not
I understand that, but they happen to do a fancy thing here, but the underlying motive is to know what it takes to generate, to track actually.
So you say it's another challenge for the controller.
Yes, so if we can make this go barrel roll, then maybe using the same pipeline, we can make it do those kind of motions where sir was mentioning that how a lion jumps 2 pounds to get an object. So they just wanted to demonstrate.
You know, this jumping river or something like
Yes.
that. So that is not a normal distance, it's a very highly agile distance. So it makes sense, right?
Sir, and also jumping
Even,
from
you have shown certain videos where it walks sideways, it does certain things.
yes,
So they were not very attractive to me because, according to me, one of the fundamental aspects of robotics is actually getting motivation from the animal kingdom.
yes,
And when you try to do, you try to do something which animals do not do, and they are not even useful. It's like we do circus, we want them to do something. So that is right. It's a question of motivation, nothing more.
just like
In
yes.
either view, I would have said that because when saying we are going to work for defense, and if you want to fake that you have been shot down, right? So you just go down from the hill, right? Go down the hill, put up the hill, stand and walk.
So like that, and if I want to jump, if I want to make the robot jump from a particular height, how do I do that while minimizing the damage to the robot? That so this approach is for that. That how should the robot? So sir, if I generate a reference trajectory and the robot does not track, or the reference trajectory that is generated, it is not consistent with the dynamics of the robot, it will not come in contact.
You do this maneuver and then maybe it is on a hill and you cannot control it. Anyway, let us not argue on that.
Yes.
So they
got the,
They implemented this.
they implement it, it's not you.
Yes,
That
sir.
is always there.
So
So it not depend.
they happen to test it for a barrel roll, but the underlying motive is to generate dynamic motions. So the first pass they used complete dynamic model with they use rotation matrix to represent the orientation and not the Euler angles in this case. And the cost and the constraints for the first pass with approximate model is by using this cost function and the initial final condition constraints. The feed position constraint, where in this case they use a spherical constraint instead of a cuboid or a cube, and they discretize the system dynamics and they use that discretized model as the constraint to enforce the system dynamics even approximately. And also, while discretizing this the rotation matrix, they cannot use directly oil forward or any other discretizing technique. They had to use a proper approach that is consistent with SOT manifold. And also, the quantity timings they optimize by specifying implicitly in their constraints. And in the cost function, they penalize three quantities. One is the angular velocity, other is the contact force, and the last one is the orientation error. As orientation error is defined as the logarithmic map of the difference between the current and the required rotation operated by a V map. So what it gives us essentially is the V map is a mapping from the Lie algebra of the SO3 manifold or the SO3 group to the R3 series. And also we have been using the other operator, that is the inverse of the operator at certain places. One of which is while defining the orientation dynamics and also while discretizing the orientation dynamics. So this gives us, this first pass gives us the contact dynamics and an initial guess on the reference trajectory. And the second pass was then used. No, sir, it is a skew symmetric form, skew symmetric matrix corresponding to the angular velocity vector. Yep.
Now, is it related to orientation vector that we operated?
No, sir. In the context of SO3 manifold, it gives us the orientation vector. Okay, as example, in this case, it is giving us the orientation error because we are using two rotation matrices here. So, if we use only one rotation matrix, we take the log map and then we use the V operator.
Oh, that is done.
So what's logarithmic map? V operator?
Yeah, V operator.
So, this takes from the skew symmetric matrix to the vector form of the matrix.
Axial. Use axial of the. It's basically the axial of a skew symmetric matrix.
This is axial vector of the skew symmetric matrix.
You can write a matrix and show them.
Skew symmetric matrix, I know it comes in context of R dot. R dot or transpose is a skew symmetric matrix.
Yes, sir.
There you are talking about R, not R dot. It's putting up not able. You try to show me.
Yeah. Sir,
No, that is fine.
Yeah.
That is R dot or
This
transpose.
question is,
That is R dot or transpose.
log you have written R reference
yes.
and R transpose.
Yes.
So R reference K, both of that is fine. What is K there?
So K is for that particular time.
That is fine.
For a particular.
There are two rotation matrices, so that I can understand. Okay, then how do you extract in so-called orientational error and making it into a axis? That is a Riemann or whatever vector.
So this R dot R transpose.
What is because K is there, so step is there, right?
R dot,
R, so it's R ref at K,
that is the
Dot.
3x3 matrix.
and this also 3 by 3 matrix.
Yeah, dot, what is dot going to?
So that is.
Sir, it is the operator for that particular SO3 group. The operation defined for all the rotation matrices, the matrix multiplication.
No, that is matrix multiplication.
Yes.
Okay. Fine. So R transpose is another 3x3 matrix.
Another 3 by 3
What is
rotation
that
matrix.
operator doing? Can you show me an example how that converts that into
Yeah.
R3?
Yeah, so sir, the logarithmic map.
And that happens before log, right? You take
No, no, after taking the log.
Okay.
After taking the log, so if I take the log map for any rotation matrix or any rotation matrix, then is if I write the exponential form of the rotation matrix like this. So by taking the log, I get finally this skew symmetric matrix.
You can write it. Okay, omega hat is this.
Yeah, so hat is the skew symmetric form, and when we apply the V operator on a skew symmetric matrix.
Omega, I would prefer you theta there because it is not omega represents angular velocity. So this is constant
So this is-
entity.
Yeah.
Okay.
So because this whole term, when we use the V operator, it converts from the symmetric form to a simple 3D vector where it can be written omega 1 t omega 2. So,
Can you hear me? Hello.
so this is how they define the orientation error in this case.
Can you hear me?
And so that concludes the first pass of their algorithm. The second pass, they do not optimize the contact timings, but they optimize the trajectory by now this time using full dynamic model, the full body dynamics with no slip constraints on the field. And the cost function at the constraint for this pass are as defined. So there is a terminal cost and the running cost for the whole points.
Four-legged,
For the same robot,
not humanoid.
not humanoid. This is a four-legged.
Because humanoid upper body model is more complicated. That's the problem.
Yeah, so this-
There is the complication is only because of the four legs.
Yeah, four legs. Their
Otherwise,
coordination.
you would probably consider them as rigid body, right?
Hmm?
The main torso.
Yeah, the main torso is rigid. That is rigid. So they use this cost function with the constraint, and most of the constraints are similar to the previous pass, but what extra method they use is constraints on the joints and some other geometric constraints that check for collisions within the limbs of the robot and also collisions with the obstacles. So after generating the trajectory, the controller that they use to track that trajectory includes the feed-forward term of that controller includes the desired torque that are output of the second pass of the full body trajectory optimization with a feedback, a KD, a PD feedback curve on the feet position velocity. So that is what constitutes.
Basically a model based, sorry,
Yeah.
more of,
So this tau d they get from their optimization. Yes.
So this QN, I did not understand. What is QN?
Qn is the configuration at last step because we will discretize the trajectory at different points, right? To do trajectory optimization. So this is the terminal cost.
So this Q is, so you are doing using this protein-based model or it is from?
It is the full body dynamics. So this Q contains the body position, orientation, and the joints.
and including the forces that are at the
Feet,
feet because
yes.
of the contact.
Yes.
If they are in contact, there will be a finite force. If they are not in contact, then it will be zero.
Yes.
Then, I wanted to ask this, Q if it has X, Y, Z and thetas together,
Hmm.
and then they come in vastly different magnitudes. So when you do Q transpose Q, then your optimization cost function they get in,
No.
you have quantities with vastly different magnitudes. Then
There is some condition number may get affected, some matrix.
so this Q, generally if you are using this floating base dynamics, then you could have X, Y, Z of the floating base, and then all the Qs respect to that floating base.
Yeah, so when we are writing this, we are not using a floating based representation. In this second pass, we only use the complete dynamic model.
No, writing, floating base, you mean to see that you are writing an equation in the body frame, right?
thing is we can, so a body in space, we can write equation of motion. Yeah, so if it is fixed to the ground, suppose one of the legs is on ground, then we start writing through that polaroid, or we directly assume the as circle.
What is the
In the body reference is space reference, but we directly start with the coordinates of one of
The body frame, I think life will be simpler. If you are writing with reference to some inertial frame, then the distances, some distances will be large, and then we'll get into
also since it is moving, so there is no fixed reference point from where you write it.
No, no, it's so we saw that S and E, right, for single digit body. So the top three were the R double dot, bottom
Yes.
three were the.
For the orientation directions.
Yes, you will have all the stuff, right? Some of them would be R coordinates, some of them would be the angle coordinates.
Yeah, so you will have all these along with the joint coordinates.
Correct. So,
Yes.
He's saying the scales are different, right?
so one of them is length dimension, one of them is angle dimension.
Yes.
And then you are taking magnitude of them together.
Yeah.
So does that create some problem?
No, that won't create any problem because it is not a matrix, it is a vector always. So all the length dimensions.
See, one is in meters or kilometers, one is in 0.2, 0.23,
But still,
one is
kilometers and radians, that is the problem. Even mm and km is okay. But
no,
then
size, the range,
Correct.
not the unit. That is why I use the 1,000. One of the things will change in 1,000, another will change in favor between +1, -2.
Yes.
So whether you are on ground frame or body frame, this problem is going to be there.
Yeah.
Yeah.
In body frame, for the way I think it will be simpler because those large distances are no longer. So everything is measured from the center of mass. And it is a single digit body, so you are forgetting the limbs.
No, sir, this is not single digit body.
So this is full
This is full digit
So
body.
they say that
So that
we
is
are
when the
moving away from
theta is coming to picture. There the scale is different, and
So what you are saying it is something
all
that
of them are only
needs to
joint
be.
variables, right? Because all of them are revolute joint. So all of them are fundamentally their joints are only theta.
Say that there will be some 1 radian or 2 radian.
all these are not revolute. That's what I want to say.
All them are revolute.
All these are revolute.
But equation of motion will have the center of mass coordinates.
That is only x
No,
y
that gets observed. The independent variable, the generalized coordinates are basically joint space, which is nothing but all of them are theta here, joint radians, because there are no prismatic kind of joints here.
Yes, sir, there are no prismatic kind of joints, but this cube contains the center of mass, position and the orientation also, along with the joint angles, to fully specify the body.
Have you
Why those two? Because they are interrelated, right? It's forward and inverse kinematics, isn't it? So either describe it in its joint space.
Yes, sir.
Once you have that related to joint, these are not independent variables,
Yes.
right? Independent variables are the joint variables.
Yes.
So your CG and all other aspects,
Yes.
they are not that variable. They get in that equation.
Yes, sir.
So if you write the equation as say it's a simple 1 degree of freedom. So you'll get m into L into cos theta or whatever it is.
Yes.
Right? So the net, the CG will not change.
Yes. But sir, when the base moves, that is happening.
No, what if you have written it in a robotics perspective?
Yes.
Okay, what I write as each individual link or the body.
Yes, that is
Okay,
one way to
each
represent.
individual rigid body. It is a multi-rigid body system.
Yes.
Each individual rigid body, I will have its parameters, which are mass, its center of mass, its inertia about its center of mass.
Yes.
This is what is important.
Yes.
That will not change in its own frame of reference.
Yes, that will
Right?
change. Yes.
So that will get in somewhere. If you look at the equation, then what happens? The equivalent center of mass, equivalent inertia, that is function of joint variable. But independent variables are only joint variables. That is what should come in QA.
Yes, sir. What I'm trying to say is that along with the joint variables or the joint angles, because even if I fix all the joint angles, the base, the torso of the robot can exist anywhere in a 3D space with any orientation.
They don't write it in the traditional way. That's what.
Yeah, that is
The regular robotics, the manipulator robotics,
Yeah.
is generally all theta.
Because
But
in
it is a bit different than manipulator robotics. The manipulator itself is floating in space. So that base equation of motion is also
should also be added.
no.
The
As
base
a
is
whole, you have one single position and orientation of the whole body. That is, see, it is more like suppose you have a manipulator analogy. Okay, so it is like entire manipulator is now floating.
Yes.
Okay, so then I can say that. So entire it is like base itself is floating.
Yes.
So your base is not fixed. That's it. You
Yes, sir,
have
but-
just two more additional degrees of freedom.
Sir, 6.
By 2 I mean 3 plus 3. By
Oh,
2
yeah,
I mean
yeah.
one positional degree of freedom for entire body.
Yes.
Right? That's all. That is fine.
Yes, sir. So that is what I'm saying is also included in QNs along with the joint variables.
Joint variables.
Joint
that
angle.
is complete degrees of freedom. Joint variables which are all theta.
Yes.
Evidence. Plus position and orientation of the entire
Of either the entire robot or the torso.
yeah, some representative.
Some representative
Yes,
one.
that we don't care.
Yeah.
I mean, of course, to solve you will care, but I mean, philosophically, I don't can make
So
anything.
this Q does contain the joint variables and those boundary degree of freedom. So
Check the chat box. I think Mangal sir wants to ask a question. Can you ask Mangal sir again? I think Avinash messaged me. Mangal sir asked.
no, sir. He said that Mangal sir probably wants to ask a question, but
Yeah, Samarth messaged me that.
He can ask from his phone, that is easier, no? If it doesn't work that way.
yeah.
We can put the phone on speaker mode and.
Yes. So after generating the trajectories to track, they use a PD feedback for the feed forward torque, and they use a PD feedback on the joints to calculate the total torque. So the major takeaways are that solution trajectory optimization based solution using approximate model gives contact timings and good initial values to use then with the full body dynamics. And the second key takeaway is that full body dynamics is crucial when we want it to perform highly dynamic motions. So, how about go there on?
Yes, sir.
So after generating these kind of trajectories, we come on to what are the different approaches of tracking these trajectories. So to track these trajectories, what many people have proposed is, many researchers have proposed is separate controllers for legs when they are in swing or when they are in stance. So in this particular paper, so they check whether a leg is in swing or in stance by employing pressure sensors at the feet, and based on the threshold value that they have set, they decide if a feet is in contact or in stance, or in swing, and they use the first order filter to estimate the ground height, and then for leg that is in swing, they calculate the desired position of the leg with respect to its hip as by a combination of two heuristics that have been defined before. The first one is the Ribot heuristic, and the second one is the capture point heuristic with a scaling parameter. And by given the swing leg positions, the position of the main body is calculated by using this equation where the weight of every leg is defined based on its contact state, whether it is in stance or in swing. If it is in stance, the leg is weighed more, and if it is in swing, the leg is weighed less. And based on these dates, the position, the desired position of the main body is calculated, and the z position of every feet, the trajectory for the z position of every feet is kept constant in this approach. Now, coming on to the stance leg control, they define a simplified controller model where they define these desired external forces and torques as this heuristic. This is not a model-based approach to design a controller model. So they design this model with a feedback on the body position and body rates, and to track the given velocity, given horizontal velocity, to compensate for the gravity force, and to track a given yaw velocity, and to keep the roll and pitch velocities to be zero always. So they made this heuristic model. They use these desired values in their controller model, and then they make a quadratic program that so they define a quadratic program where they use the controller model as sort of constraint inside the cost function itself, with a regularization term subject to the friction cone constraint and minimum friction constraint, minimum contact force constraint. So the major work that came after all this in this paper was that by interpolating between all these parameters for different trajectories or different gates, they were able to perform transition between all these different gates while doing the motion. So this was the key takeaway from this paper, that parameter interpolation works for online gate transition for dynamic motions. And this is one of the approaches to